Hi guys, so we have now finished our work on light and I want to now move on to sound. Now, I know we've already done a little bit of work on the speed of sound, but we haven't really talked about what sound is and some of the other important factors that you need to know about sound. So that's what we're going to be doing in today's lesson. So let's look at the lesson objectives. After today's lesson, you should be able to explain what sound is and what determines its pitch and volume. You should be able to recall the human range of hearing. And you should also be able to understand what ultrasound is and how it is used. So I want to start with a recap of waves because I'm going to be using lots of terms in this lesson and I just want to make sure that you're definitely familiar with what I'm saying. It's been a little while since we went over this, so I just thought we'd start with a recap. So to start with, we've got two broad types of waves. They are transverse and longitudinal. So let's have a look at these in turn. So the first one is a transverse wave. Now, if you remember the work we did on this, a transverse wave is a wave in which the particles are vibrating at right angles to the direction in which the wave is moving. It's probably easier if I show you a diagram. Here we've got a particle moving in the vertical direction, whilst the wave itself would be moving in the horizontal direction. And the wave itself would actually look something along those lines. And if you remember, we have both crests, so that's everything above our rest or mean position, and here is a trough, which is everything below the rest or mean position. So here's our transverse wave. There's a few other terms we need to be familiar with. So I've already used this just a second ago, and that was the rest or mean position. So if these particles didn't have any energy, if they were just kind of at rest, that is where they would be, sat on that line. However, because of the fact that they've been excited, because they're oscillating, they're obviously moving above and below that position. If you were to take the position, the average position, hence the word mean, that would also be that rest line. So we sometimes call it the rest position, sometimes the mean position, the average position of the particle. Other things we need to consider are what the amplitude is. Now the amplitude, the definition is the maximum displacement from the rest or mean position. So we can either have that above the rest or mean position as indicated here, or it could be below. Those two would be the same. What it's definitely not is the distance from the top of a crest to the bottom of a trough. That would be twice the amplitude. So the amplitude is the distance from the top to the rest position or from the bottom to the rest position. The next term we need to be familiar with is the wavelength. So the wavelength is the distance between two successive peaks or troughs. And so that's indicated here by these dashed lines. We use the symbol lambda to denote wavelength. Also worth noting that both amplitude and wavelength are measured in meters. The next definition I want you to know is frequency. So this is the number of complete oscillations per second. I'm going to show you an animation in a second. I'll try and explain that a little bit more. And the third term I want you to be familiar with is the period. So that's T, and that is the time for one complete oscillation, which is measured in seconds. So let's have a look at these terms, frequency and period, in a little bit more detail, just so that you properly understand what I mean by them. So I'm going to use this animation again to just clarify what I mean by the terms frequency and period. So we'll start with frequency. Now, in order to do this, we need to have an understanding of what we mean by one full oscillation. So one full oscillation is the motion of this particle from one position in its vibration back to that same position. So, for example, we might go from the top to the bottom and back again. So start, stop. So that was one full oscillation, but it could be from any position. So we might, for example, go start, stop. So that was from the bottom to the top and back again. Or we might go start, stop. And so that was from the middle to the bottom to the top and back to where it started. So that's one full oscillation. Now the frequency is the number of full oscillations we get in 1 second. So if I've got a frequency of, say, for example, 50 hertz, we're going to get 50 complete oscillations in 1 second. If I've got a frequency of 1 kilohertz, so 1000 hertz, that's going to be 1000 complete oscillations in 1 second. So what's the period? The period is the time it takes for one complete oscillation. So how long does it take to get from the bottom to the top and back again? Now actually with this one we can time this. So just give you a couple of seconds to get your phone out if you can. Hopefully you're not using your phone to actually do this. And we're going to time the time for 10 oscillations. So I think it's moving too fast here for us to do one, so we're going to do 10 full oscillations. So get your timer ready and we are going to say start. 1, 2, 3, 4, 5, 6, 7, 8, 9, and stop. And I got 20 seconds there. I actually got 19.98 seconds. So there's a little bit of human error there. But I think we're safe to say that we're getting 10 oscillations taking 20 seconds. Now, if I've got 20 oscillations being equal to, I have to, excuse me, we're going to do 10 oscillations, I said, doesn't it, in 20 seconds. One oscillation is going to be equal to 2 seconds, and therefore our period T is 2 seconds. Let's go back to the frequency. Well, if it's taking 2 seconds to do one full oscillation, how many oscillations are we getting in 1 second? The frequency is going to be equal to 0.5 hertz. So within 1 second, we're only actually getting half an oscillation. So that's one way of thinking about frequency and period, but there's another way of thinking about it as well, and so we're going to look at that on the next slide. So we've just discussed how we can think about frequency as the number of complete oscillations per second, but we can't always see the particles oscillating. In most cases, we're going to see a wave moving along like that shown here. So how do we get the frequency of a wave like this? Well, we can think about frequency also as the number of waves that pass a given point per second. So that given point for me is going to be this arrow. Now, I've got my phone set up with a timer now with a 10-second timer. And so what I'm going to do, I'm going to start that when one of these crests pass my arrow, and I'm then going to count how many crests pass that point in 10 seconds. We can then divide that by 10 to find out how many passed in 1 second. So let's go ahead and do that. So we're going to go start. That is 1, 2, 3, 4, and we've got my alarm going off. So we've got there 4 crests passing that point in a period of 10 seconds. So if we've got 4 waves being equal to 10 seconds, then we are going to have we're going to have 0.4 waves in 1 second, i.e. the frequency is equal to 0.4 hertz. So the frequency of this wave is 0.4 hertz because we're getting 0.4 waves passing our point every second. Okay, so that was transverse. Now let's have a quick look at longitudinal. So in a longitudinal wave, the particles oscillate parallel to the direction in which the waves are moving. So in this case, the wave is moving from left to right, and the particles are oscillating in line with that, so in parallel to that. Now, rather than getting a series of crests and troughs, we're actually going to get a series of compressions and rarefactions. So compressions are the regions where all our particles are bunched up, they're really close to each other, and the rarefactions are where they're spread out. So now that we've done our recap of waves, let's go on and try and answer the first of our questions in today's lesson, and that is, what is sound? Well, at a very basic level, sound is a vibration. So it's the vibration of air molecules that travel as a longitudinal wave. So this speaker over here is vibrating. That is causing the air molecules in front of it to also vibrate. Now those compressions are going to be moving along in this direction. Just want to stress it's definitely not the particles. each individual particle is simply going to be oscillating backwards and forwards. So if I choose one, say for example here, all that's going to be doing is going to be oscillating backwards and forwards around that fixed position, but the compressions themselves are going to be moving from left to right away from that speaker and towards the ear. That's then going to kind of cause your eardrum to vibrate, which causes the 3 bones in your middle ear to vibrate, and that then causes the fluid in your inner ear to also vibrate, which then gets picked up by your cochlea. Which is then connected to your brain by a series of nerves for you to actually be able to detect that sound. But at its core, sound is a vibration. One thing that's probably quite important to note here is because of the fact that sound travels through the air due to the vibration of those particles, if there are no particles, i.e. say for example a vacuum, sound cannot pass through it. So you do not get any sound passing through a vacuum. I'm always quite infuriated by sci-fi films where you see a spaceship blowing up and you hear a huge bang. That wouldn't happen unless you were in it, and of course then you'd be dead. But you know, if you were viewing that from another spaceship a distance away from it, you might get a shockwave hit you. But you wouldn't actually hear any sound from it because you know, there's no vibrating particles, so sound cannot travel through a vacuum. So before we move on, I just want to just make a point because it often confuses people. Sound is very definitely a longitudinal wave, but because of the fact that when we look at a series of compressions and rarefactions, it's very difficult to take measurements of things like amplitude and wavelength. We never show a sound wave on an oscilloscope or on a screen as a longitudinal wave. We always show it as a transverse wave. It's not a transverse wave. We are just representing that longitudinal wave as a transverse wave because then it's much easier to be able to take things like wavelength and amplitude from it. So if you see diagrams in the rest of this lesson of the wave being represented by a transverse wave, that's purely to make life a little bit easier for us. It's not actually a transverse wave. You'll notice from this diagram that all of the crests of our transverse wave perfectly line up with the compressions. So where we've got a compression, we get a crest, and where we've got a rarefaction, we get a trough. Okay, so frequency and amplitude. How is the frequency and amplitude going to affect the sound that we hear? Well, I would normally show you this by generating a sound in the lab and fixing it up to an oscilloscope, but because of the fact that we can't do that, I'm going to use an animation. So in the Show My Homework that I've set, there is a link to a PHET animation, or it's a simulator that I want you to go to and have a play with. So if you go to Show My Homework, follow that link, or just type this into your browser and just have a bit of a play with that simulator before we move on. So pause the video, go and do that, and then come back to the video when you've done it. So, having now played with that simulator, I'm hoping you can all see that there is a very clear relationship between the frequency and amplitude of a wave and the sounds that we actually hear. So let's start with the frequency. I'm hoping that you all saw that as you increase the frequency, the pitch also increased. So the higher the frequency, the higher the pitch that we hear. So I've got two waveforms here. The one on the left has got a high frequency, the one on the right a low frequency. They've both got the same amplitude. Which one is going to be a higher pitch? A higher pitch as opposed to a lower pitch. Well, the one on the left has a high frequency, so it's going to have a high pitch, whereas the one on the right has got a low frequency, so it's going to have a low pitch. Let's now have a look at the amplitude. From that simulator, I'm sure you all saw that the higher the amplitude, the higher the volume. So the louder that sound is. Again, let's have a look at this diagrammatically. So I've got two waves here. They both have the same frequency, but the one on the left has got a large amplitude. The one on the right has got a small amplitude. The one on the left is therefore going to be very loud, whereas the one on the right is going to be really quiet. Okay, so really important that you get these diagrams into your book. Really important that you can tell the difference between kind of the different sounds by looking at these diagrams. If you're given one of these diagrams to compare, you need to be able to say which one's going to be a high pitch, which one's going to be high volume, etc., etc. Okay, so there's a couple of different types of sound that I want to run through with you. So far, we've been looking at sounds that have a single frequency or a single kind of pitch. So this tuning fork that you can see at the top here is producing a really uniform waveform that has a constant frequency, and that's just going to be the kind of sounds that you've already heard. However, when that hammer is being smashed onto something, we're actually getting a large combination of lots of different frequencies and amplitudes, and so that's going to be not as going to be as harmonious. It's not going to be a nice sound. So if you want to just kind of like a continuous tone, a continuous pitch, we're going to need a nice clean waveform like the one shown at the top. Now, when it comes to musical instruments do not play a single frequency. They play a set of frequencies that are all in harmony with each other. So they're normally kind of multiples of a certain frequency. So you might say, for example, have 400 hertz and then 800 hertz. They would actually kind of add together to make a new sound. And we can see here that kind of different instruments are going to have different combinations of those kind of frequencies and wavelengths. So the flute here has got one type of waveform that's lots of different frequencies all being played on top of each other, and the clarinet sounds different because it's got a different set of frequencies and wavelengths all kind of like sat on top of each other. Musical instruments do not play a single frequency. I'm going to play you a video in a minute of just a single tone being played right down from 0 up to 20,000 hertz. And it isn't a pleasant noise to listen to. In order to get like a nice musical instrument sound, you need lots of frequencies all playing together in harmony with each other. So in regards to musical instruments, you tend to find that the bigger the musical instrument is, the lower the pitch that it creates. So the diagram on the left is a small violin. That's going to produce a very high pitched sound, whereas the double bass on the right hand side is going to produce a much lower pitch, a much lower sound. Okay, we've done a little bit of work so far on reflection, refraction, and diffraction. I just want to make sure that you understand that sound can be reflected, refracted, and diffracted. So in terms of refraction, you often find that because of the fact that you've got different layers of air, this doesn't tend to happen on a windy day where all those layers are getting mixed up. On a relatively still day, you've got different layers of air, each one at a different temperature, and as sound moves from one layer to the next, you're going to get refraction taking place. So refraction does occur in sound. You might have heard this. Sometimes you might be kind of in your garden and you can hear a noise that is really far away, and that is because of the fact that the sound, as shown in these diagrams here, has been effectively undergone total internal reflection as it's tried to go from one boundary to the next, and it's come back down to you. I used to live up in Mofont Village in St Martin's, and on a really still day I could actually hear the tannoy system down at the harbour, and that was because of the fact that refraction was occurring, total internal reflection, causing that sound to can be bounced off one of these layers of air. Reflection also occurs. Obviously, a reflection of sound is what we call an echo. And finally, diffraction definitely occurs. We've got here a radio around the corner from a guy. If diffraction didn't occur, he would never hear that. But because of the fact that sound does diffract, he is able to hear those sounds around that corner. Okay, can we hear all sounds? So here I'm going to play you a video. I wouldn't recommend that you have your volume up too high. If you've got a dog in the house, I might try and get them to leave the room, because they might not necessarily like this when you get up to the higher pitches. But what I want you to do is just listen to it and just try and judge, not exactly because it moves quite quickly, but just try and judge at what frequency you start and stop hearing the sound being produced. So here we go, we'll play this video. So having watched that video, you should now have an idea of your own personal range of hearing. So the range of frequencies that you personally can hear. Now, you should find it should be roughly in the region of 20 to 20,000 hertz. So this is the range that I want you to quote if you're ever asked this in an exam question. So from 20 hertz up to 20,000 hertz. Now, in reality, not many people are going to be able to hear sounds as high as 20,000 hertz. If you were a newborn baby, you would be able to, but the older we get, the effectively more damaged our hearing becomes, and the lower that upper end of that kind of range becomes. So you guys probably would have found yours goes up to about 17,000 hertz. You've already started damaging your hearing by listening to headphones too loudly, etc. And for me, it's going to be even lower. It's probably around the region around 16,000 hertz. If you were actually in class, I do this experiment as a live demonstration, and what I normally do is get everyone to put their hand up and then put it down when they stop hearing the sound, and I am always the first person to put my hand down. And interestingly, when you then ask the next few people to put their hands down, whether they listen to a lot of loud music, the answer is always yes. And it's the guys that don't tend to listen to music very loudly on headphones that put their hands up for longer, because they've not damaged their hearing as much. But the point is, everyone's going to be different. But if you're ever asked the question, what's the human range of hearing, you need to recall 20 to 20,000 hertz. Now, anything above that 20,000 hertz threshold is what we call ultrasound. And I'm going to talk more about ultrasound in a second. Just interestingly, different animals have different ranges of hearing. So things like dolphins and bats tend to hear much higher frequencies. Things like whales can actually hear much lower frequencies. Obviously, a dog whistle, I'm sure some of you have probably heard a dog whistle in the past. You blow a dog whistle, you can't hear it. It's above 20,000 hertz, but your dogs can. Hence why I asked you to get your dog out of the room if you were just doing that video, because it can irritate them quite a lot. Okay, so let's have a look at a little bit more about ultrasound. I think the first thing I want to mention is the fact that, like with light passing through a window, we get partial reflections when a sound passes from one medium to another. So if we allow an ultrasound to pass through a material, every time it gets to a boundary between two different mediums, between two different materials, some of that sound is going to be reflected. Now, if we know how fast that sound is traveling through each of the materials, we can actually work out how far away those boundaries are from the emitter receiver. Okay, so that enables us to do a few things. I'm going to go through them now. So the first one is the use of ultrasound in medicine for prenatal scanning. So when an expecting mother goes to the hospital to have the health of their child checked, they are going to use ultrasound. So they're going to place an emitter receiver on their stomach. That is going to send a sound wave through their skin, goes through all the different layers of kind of muscle and sinew and fat, etc. And then we'll go through to the womb, then to the baby, etc. And every single time it gets to one of those boundaries, it sends a partial reflection, which is then picked up by the receiver. And because it knows exactly how fast those waves are traveling, it can actually effectively draw a picture of what's underneath all those different layers of skin and muscle, etc. So the big question here is why ultrasound? Well, there are two reasons. If you think back to the work that we did on diffraction, we get the most amount of diffraction when the object through which the wave is trying to pass is roughly similar to the wavelength of the wave. Now, we don't want diffraction to occur here because it's going to distort our image. So we need to make sure that our wavelength is much, much smaller than anything that we are trying to take an image of. And so therefore we want a really high frequency to give us a really low wavelength so we don't get any diffraction. So that's one of the main reasons. I think probably for this one, more importantly, is the fact that if we were to use X-rays, that could actually harm that unborn fetus. Whereas the sound waves, there have been loads of studies into this, and there's absolutely no link between kind of the use of ultrasound and any harm being done to the baby. So it's far, far safer. So another use of ultrasound for both humans and for animals is the use of echolocation. So I've got here a bat sending out a sound. It's bouncing off that insect, which the bat is then hearing, and using that kind of the time difference, the amount of time it takes to get from the bat to the insect and back again. That bat can work out exactly where and that moth is, how far away it is, and it can capture it. Dolphins use the same thing to catch fish, as do we. And a fish finder on board a boat is going to be sending out a sound wave, bouncing off a shoal of fish, coming back up to the fish finder, and it's kind of using the speed of sound in that fluid, the time difference between emitting the sound and hearing the echo, to actually work out how far away those fish are. Why are we using ultrasound? Again, it's because of the fact that we get very little diffraction when we're using very high frequencies. And if we get diffraction, we're going to get a distortion in the image that we're getting, and we don't want that. Okay, another use of ultrasound is for detecting cracks and faults in solid objects. So on the left hand side here I've got a display which is showing this use, whereas on the right hand side I'm going to try and explain to you how it works. So I've got here our emitter receiver put up against a piece of material, and we're going to send a wave out which is going to bounce off the backside of that material and get back to the emitter receiver. So on the screen we're going to get something that looks a bit like this. I've stretched out what we're seeing on the left hand side here. That first spike is actually the initial sound being made, and the second spike is actually the reflection that is being detected after it has bounced off the back. Now we can actually work out how thick that material is if we know how fast the sound is travelling through that material by looking at the time it took to get from the initial sound to the reflection. Now, if we now introduce a crack into our material, now not only are we going to get our initial sound and we're going to get a reflection off the back of the material, we're also going to get a reflection off the crack. And so that middle spike there is actually indicating that there was a crack in the material. Now, this kind of technology is used in lots of different industries to be able to try and find very small cracks inside metal. So things like the aviation industry, trying to find cracks in aircraft structure. You might also get it on things like large buildings like bridges. So kind of engineers will go out and use this technology to try and find very small cracks in pieces of metal. Okay, so just to summarize what we've done so far, you should now be able to explain what sound is, i.e. a vibration, and you should be able to explain what determines its pitch and volume, i.e. the frequency and amplitude of that wave. You should be able to recall the human range of hearing, that's from 20 to 20,000 hertz. You should understand that ultrasound is a sound above the human range of hearing, i.e. anything above 20,000 hertz, and also give examples of where and how it is used. Okay, so in our next lesson, I'm going to give you some questions relating to ultrasound and its use. And it's going to kind of tie together all the work we've done so far on sound. So good luck with that next week.